Thank you for your attention. And
Taku Gunji, and he will talk about new physics in ALPS.
Okay, so thank you very much for inviting me to present this talk. So new physics searches in heavy ion collisions in ALPS. Okay, so I would like to, this is my outline of my presentation, the ALPS experiment and the ongoing ALPS upgrade for round 3 and round 4. And then I would like to talk new physics searches, status and prospects. So I picked up several cases, the dark photons and Jebb scale dark gauge boson, and the anti-nuclear production and the implication for cosmic dark matter. Of course, I mean, ALPS has a lot of activities like UPC physics, but I didn't include in my presentation. And then I'd like to briefly mention the ALPS 3. So this is another upgrade beyond the 2030. And then I summarize my presentation. Okay, so the ALPS is one of the experiments at the Red Sea and dedicated to heavy ion collisions. So this is a place of ALPS. So the main one of the main goals of this heavy ion collisions in ALPS is to characterize the strongly interacting quark-gluon plasma. So just after the collisions, so the new state of matter, the quark-gluon plasma is formed, and where the matter is composed of deconfined the quarks and the gluons. So we would like to understand what is the nature of this quark-gluon plasma. So I would like to explain what we are doing. So yeah, so we did a lot of measurement to characterize the quark-gluon plasma, and this is a recent the experiment and theoretical like activities. So there are some like measurement. This is yield, the pion kaon proton, and this is the so-called B2, the azimuthal anisotropy. I mean, this is the indication of correctivity of the system. And also this is a mean PT and mean PT fluctuation, and this is the data point. And then if we compare with the hydro-based like simulations and do some Bayesian analysis, and one of the parameters is this eta over S. So this is the viscosity to entropy ratio. And then from this measurement, so we can constrain the eta over S, the shear viscosity over entropy ratio. And this is the water, and this is the helium, and this is the quark-gluon plasma. So this is known as a function of the normalized temperature with respect to transition temperature. So we see that the quark-gluon plasma behaves like the nearly perfect liquid, and quark-gluon plasma has the smallest specific shear viscosity. So this is what we have learned from the heavy ion physics. Okay, so this is just a general introduction of the of our one of the main physics. So then I come to the explanation of ALPS experiment. So ALPS is designed to carry out the comprehensive studies of hadrons, electrons. I'm sorry, no. Sorry, in my display. I'm sorry, in my display, I see a lot of other stuff, but okay, now it is gone.
We see only your slides. For us, that's fine.
Yeah, but okay, but my display, I mean, in front of my slides, I see the participant and so on, but now okay, sorry, I changed. Okay, so the electrons, muons, heavy flavors, photons, and jet produced in heavy ion collisions. So this is our experimental setup. So from the collision point, so there are inner tracking system. This is a silicon detectors, and then TPC, TRD, time of flight, and then EM call, and everything is in the L3 magnet and in forward direction. So we have the forward muon spectrometer. And this is an event display of one heavy ion, one lead-lead collision. So we see a lot of particles, and our detectors can identify one by one very precisely. So we have excellent PID performance, and also we can measure jet, and excellent the vertex capability. So we can measure displaced vertex from heavy flavors and the diesel decays, cascade, and gamma conversions. And we have the efficient low momentum tracking down to 150 MeV. This is also another important point for ALPS. So this is Alice data taking history from run 1 and run 2. So we accumulated so far like around 0.8 nanobarm inverse for heavy ions. And also we accumulated xenon, and also we do a lot of physics in PP and period collisions. Even though the delivered luminosity is much below compared to the Atlas and the CMS. Okay, so now we are doing the Alice upgrade. So the major upgrades are the replacement of inner tracking system and the new inner tracking system, which are composed of all CMOS active pixel sensors. And also we already installed. So we installed the forward muon tracker. So this is placed in front of the muon absorber to improve the vertex and momentum resolution for forward muons. And for the central barrel, the end cap chamber in the TPC are replaced from wire readout to gem readout. And also the new electronics allows to read out data continuously. So no gating grid, no trigger anymore for TPC. And another important upgrade is the new data acquisition system, so-called offline integrated system, O2. So the aim is to record the minimum bias related data larger than 50 kilohertz. So in run 2, so this was limited below 1 kilohertz. So this is a very the huge improvement for us. Okay, so as I said, the aim is to record the minimum bias related data at 50 kilohertz and collect the 13 nanobarm inverse in run 3 and run 4. So yeah, so this corresponds to the 100 times larger minimum bias statistics with respect to run 1 and run 2. Okay, so now I come to the new physics searches in Alice. The first topic is dark photons. So I don't need to explain, but dark photon is an extra U1 gauge boson and acts as a messenger of dark sector with the residual interaction to the standard model particles. So this is motivated by a number of astrophysical anomalies like antiproton spectra, the positron excess in the cosmic rays, and muon D-2 anomaly. And this is a little bit old, or maybe this is a little bit old, but okay, so this is the constraint of the mixing parameter as a function of mass. So then our target is to make some contribution in this mass range. So yeah, and also in Alice, so we have a lot of the piezoelectric decays. So therefore, we can do dark photon searches in Alice for low mass region by doing the bump hunting of prompt dark photons in large piezoelectric decay in Alice. So this is what we are going to do, or we have done. So by using run 1 data. Before coming to that, I would like to explain our dielectron measurement in Alice. So we have the good capability to measure electrons. So then naturally, of course, I mean, we can measure dielectrons with some level of the accuracy. So this is the opposite sign E plus minus invariant mass spectrum. So in proton-proton collisions. And this black one, this is the same sign pairs. So this is a kind of the combinatorial background. So we see the huge difference in very low mass. This is actually coming from exactly the piezoelectric decays. And this is the signal to noise ratio as a function of mass, and below like 100 MeV, the signal to noise ratio is larger than 1. So we have very good capability to measure to get the large samples of piezoelectric decays. And this is the corrected invariant mass distribution within Alice acceptance. This is the PT cut, and this is the rapidity eta cut. So this is the proton-proton 13 TeV, this is 7 TeV, and this is the red-red collisions. And this line shows the so-called cocktail calculation. So this is a contribution from non-hadronic sources. So yeah, we see the good agreement between measurement and also the cocktail calculations. So which means our dielectron measurement are in good control. So this is what I want to say. So now I come to the like result. This is the still preliminary result. I'm sorry, I have to work on that, but yeah. So, but anyway, this is a preliminary result from round 1 proton-proton and also, sorry, the proton-lead collisions, both proton-proton and proton-lead, 276 million event and 85 million proton-lead collisions. So we see the 92K pairs in this mass range from 20 to 100. So, okay, so by doing a kind of the like peak search, and then we extracted the like mixing parameter, and this is around 10 to 2 times 10 to the minus 3. So unfortunately, our measurement is not better than the other experiment, but of course, I mean, this demonstrates that we can do a kind of the dark photon searches at some level. And also the analysis is also ongoing. So this is the limit for round 3 and round 4. This is summarized in the yellow report. So yeah, this is based on the 6 picobarn inverse for proton-proton and 0.3 picobarn inverse for proton-lead and 13 nanobarn inverse for lead-lead collisions, where the magnetic field is like 0.5, 10 nanobarn inverse for 0.5 Tesla, and 3 nanobarn inverse for 0.2 Tesla. And of course, I mean, this introduces the different acceptance of electrons. I mean, the PT acceptance is very different for these two cases. So this is the estimated piezoelectric decays from 0 to 100 MeV. So you see that the substantial contributions are from the heavy ion data. So this is what we expect. And if we have these statistics of piezoelectric decays, so then we can reach the mixing parameter G around 10 to the minus 4. So of course, I mean, now we have the like bright future prospects that many experiments already can cover around this. But of course, I mean, ALICE can also do this kind of searches in round 3 and round 4. Okay, and so the next one is Jeb scale dark gauge boson searches. So, you know, I mean, this around from 0 to 100 MeV, so the constraint is very good, but we still have some room above like 100, I mean, the around 1 GeV, so to say. So then this 1 GeV region, so one possibility is to use heavy ion data. So this is the diagram of BS resonances around 1 GeV. And this diagram is exactly identical to the thermal radiation from quark-gluon plasma. So if the quark-gluon plasma is formed and this system is thermalized, so we expect some contribution from like quark and anti-quark annihilation, and then go to gamma, and then this goes to dielectrons. So this is one of the calculations, and we expect like this is the contribution from QQ bar and Q bar G, and this is based on the I think PHSD calculation, and this is the heavy flavor contributions. But anyway, I mean the quark-gluon plasma provides additional thermal sources in intermediate mass region, and this can be useful to search for the dark gauge bosons around 1 GeV. And actually, the earlier estimation has been done by using Phoenix GoGo data, and this is written in this paper. So we don't have any, I'm sorry, we don't have any concrete values for the parameter, but I'd like to show this invariant mass spectrum for round 3 and round 4. So thanks to the statistics, I mean the factor 10 larger statistics, so we expect to have this kind of beautiful invariant mass spectrum in the lead-lead collisions. And of course, thanks to the inner tracking system upgrade, so we can separate the prompt dielectrons and also dielectrons from like heavy flavors efficiently. So then by applying some cut to reject the dielectrons from heavy flavors, so we can expect that we see this kind of the thermal dielectron signals at LHC energy. This is the first chance to see the thermal radiation at LHC energy. So I mean, the next step is to try to estimate how much we can go. But yeah, so this is also one of the main subject in the future. So then I'd like to mention the another topic, the cosmic ray anti-nuclei production. So this is the unique probe for direct dark matter searches. So this is the predicted anti-deuteron flux, and this is the predicted anti-helium flux near Earth. So this is the secondary contribution. So this is mainly from like proton-proton, proton-helium, and helium-helium. This is the interaction of cosmic rays and the interstellar medium. So on top of this, in addition to this, so we expect this kind of the contribution from the annihilation by dark matter, annihilation of dark matter particle. So in this case, we expect the production, we expect excess in anti-nuclear flux at low energy. But of course, to predict, to estimate how much, so then we have to know the anti-nuclear production in hadron collisions and anti-nuclear absorption cross-section. So this is the most important one, and also propagation in the universe. So this is the current predictions. I'm sorry to say I'm not the expert, but okay, so the production. So this still has some large uncertainty because of the unknown production mechanism, especially at very low energy side. And also this annihilation. So, so no available data at low energies around this region. So then this introduces probably unknown uncertainty. So this is what we are going to constrain by using the ALPS detectors. So before talking about the absorption, of course, we measure the anti-helium-3, and this is about the production of anti-helium-3 in ALPS. So this is a proton-led collisions. This is a PT spectrum in proton-led collisions, and this is a PP spectrum. And by using this spectrum, so we can estimate the so-called coalescence parameter. So this coalescence parameter is defined like this. So this is a yield of the helium-3 divided by the proton spectra and the cubic of the proton spectra. So this simply tells us, how fraction of the like protons go to form the anti-helium-3 by coalescence process. And this B3 as a function of multiplicity is shown here. So this is the proton-proton point, this is a proton-net point, and this is a lead-net point. The interesting point is, so this black line, so this is this is from the model calculations, where which takes into account the size of the nucleus and also the size of the volume, the emission source. So this trend is nicely reproduced by the coalescence model. So therefore, we can extrapolate the production in the very low energy region by using this coalescence model. So then this is about the anti-helium-3 absorption. So how to measure this is quite simple. So we measure the raw reconstructed anti-helium-3 to helium-3 ratio. And we measure the anti-helium-3 in time of flight, here. And then divide it by anti-helium-3 in the TPC. So the loss of the anti-helium-3 is from the additional detector material. And this is the ratio of the anti-helium-3 divided by helium-3 as a function of P over Z. So you see, this is this blue one, this is ITS TPC TOF analysis, and this is ITS TPC analysis. And this red one, if we compare this red one, so this is a Monte Carlo Giant 4 based simulation. So there is so big difference between here and here at the low low PT region. So this is due to the fact that the cross section, the absorption cross section, in elastic cross section of anti-helium-3 in the detector material is underestimated by this Monte Carlo simulation. So by using this result, so we can extract the inelastic cross section, and this is shown here. So this is the you see, this is the okay. So this is and this line shows the like Giant 4. Parameterization used in Giant 4, And we see that, I mean, up around 2 GeV. So this is nice. I mean, agreement is good, but very low PT. So we see the steeper rise than expected from the modeling. So this is what we see. So then how this impact to the prediction of the spectra. So this is the anti-helium-3 spectra, which was based on the developed coalescence model by using ALPS data. And so now this is extrapolated to low energy. And also the cross-section, I mean, annihilation cross-section, absorption cross-section is extrapolated to lower material to mimic the universe target, the proton or a mixture of proton and helium-4. And this cross-section is shown here. So this is our extrapolation. And then by using this, so this is, we obtained this kind of the expected flux close to Earth, and this is the background component, and then this is the dark matter component. So probably this can be also useful for the to develop this kind of the cosmic ray dark matter search, in the future. Okay, so then I come to the ALPS-3. This is the another upgrade project, the next generation heavy ion experiment for run 5 and run 6. So now the ALPS. Okay, now ALPS is going to, I mean, we already submitted this in the archive. So now we are preparing for letter of intent, and detector concept is the ALPS-3. So will be consists of 10 layers, approximately 10 layers of all CMOS sensors. And the first readout to inspect the higher luminosity, I mean 100 times larger compared to run 3 and run 4. And another important point is to enlarge the low PT coverage around 50 MeV. And also we are thinking about some particular ID detectors. So probably with this setup, so now the people are working to estimate how much we can do for dark photons, LLP, and light by light scattering, and some LP, and also some like tetraquark searches, and so on, and magnetic monopoles, and so on. So this is still under evaluation, and yeah, this will be written in the upcoming letter of intent. Okay, so then I'd like to summarize my presentation. The ALPS is optimized for heavy ion physics and accumulated related data in run 1 and run 2. And now we are doing the major upgrade in order to inspect 100 times more statistics for literate. And by using these statistics, so we can open a lot of physics for a lot of new physics searches like dark photons and the Jebb scale dark age bosons. And also we can improve the absorption cross-section and so on. And also we are starting, of course, I mean, not only this, we also doing a lot of effort to measure like UPC to move forward the UPC physics and so on. And also the ALPS is now preparing letter of intent for a next generation of heavy ion experiment. And yes, so these are the main topic for new physics searches. But if you have any suggestions, proposal to ALPS-3, so then I appreciate your input. So yeah, so thank you very much for your attention.
Thank you very much for this nice overview. We have already a question by Susanne.
Yeah, thank you. I might have a suggestion about dark photons. It's best visible on your slide 11. So I was comparing the sensitivity of what you project for dark photons from pion decays for ALPS with what LHCb does. So these blue regions that go further down in the coupling than ALPS, these are from excited D-meson decays for the lefter area and from displaced searches, so searches for displaced charged muon pairs.
Yes.
And I'm wondering if ALPS can do displaced vertex searches, because from the sensitivity show here, with the prompt search, it seems likely that you could explore those regions as well.
Yeah, of course, I mean, we can try to do that. I mean, yeah, we have not done yet. So that's why we haven't put the result here. But of course, I mean, this is one of the menu which personally I am going to do. So for the moment, I don't have the quantitative answer, but yeah, so we will do. Yeah.
That's good to hear. Thank you.
Okay, Marco.
Hi, and my question is kind of related to that. So I think one of the plots, some of the plots that you showed went down to very low PT values, right? But I think they were for antinuclei. So my question is wondering if you look at, if you search for particles that, if you try to trigger on particles that are, let's say, not antinuclei, but leptons or so, or even other charged particles like pions or something, what's the lowest PT that you need? Because we found that for long-lived particle searches, one of the advantages of heavy ion collisions is that you can go down to low PTs, and it seems that ALPS can do that. So can you say something about this?
Okay, so for the moment, yeah, so you mean, okay, so in run 3 and run 4, okay, so we have the improved ITS coverage. So maybe we can try to go down to around 50 MeV, and also we can lower
50
the magnet
MeV
from 0.5 to 0.2. Yes.
Whoa,
yes.
that's very, very low,
mean,
because I think CMS
yeah.
has something like 3 GeV or something like that, because of the magnetic fields and stuff. So you're saying here to 50 MeV.
Yeah.
Oh, that's
yes,
impressively low.
Yeah, for the dielectron analysis, so we already have some analysis by using low magnetic field, and the lowest PT cut is around 75 MeV. So probably this can be a little bit lower for run 3, but yeah, so yeah, we will try. So, but we can already reach around 100 MeV. So
okay, thank you very much.
Giovanna.
Yeah, hello. Thank you for a very interesting presentation. You mentioned light by light and ALPS on your list of measurements for the ALICE 3 project. I'm wondering about, earlier data taking, run 3, 4, and perhaps even run 2 data. Is it possible with ALICE to measure those processes?
Yeah, of course. I mean, we can. Okay, so for the light by light scattering, so well, actually, I'm not the, the expert of this part, but at the time we already measure the gamma going to dielectrons, for example. So, and we see the very large enhancement of signals in very low mass. The very low PT in the intermediate mass region. So we already, yeah. So yes, so this will be developed for run 3 and run 4. So yeah, this is also one of the hot topic in ALICE. Yeah.
Okay, thank you.
David?
Yes, somehow related question. We discussed about ALPS yesterday in LHCb. I'd like to understand the photon energy resolution that you have in the region below 5 GeV, where ATLAS and CMS cannot do basically anything. What is the photon resolution that you have there? Energy resolution.
I think, I think probably such low energy region. So probably one way is to use is to measure the conversions. So I think in this case, the resolution is determined by the momentum resolution of TPC. And I think, I don't know the quantitative number, but I think this is not so bad. So I'm sorry to say this. But, yeah.
But you have the conversion probability, you pay a price there. You have to convert both photons. So you should have 4 electrons, let's say for a...
Yes, I mean, of course, efficiency and so on is quite low. Acceptance is quite low, but yeah, so this is a kind of trade-off. But for calorimeter, probably this is, I mean, almost the same or a little bit worse compared to the CMS and ATLAS. We have also the FOSS, I mean, the lead tungsten calorimeter. This is also, I mean, the same one is also in CMS, but yeah, probably it is probably the the convergence and the tracking system is worthwhile to be looked at for this low energy range.
But are you looking into already this light by light scattering and ALPS in the low mass region? Is anybody looking into this?
I don't know. I don't know if somebody from Alice can comment.
Okay.
Honestly speaking, I'm
Maybe-
not following so
Maybe
much.
I can comment, but I'm not very much aware, but I have seen one presentation at a very early stage looking into this. And about the conversion probability, so I think it's, but Taku should know this as well, it's about 10%, right? This is the order of magnitude to have a conversion detected in the TPC.
Thank you, Michael.
One question by Oliver.
Hi, maybe a bit of a curveball for you, but we had some, in Artu's talk yesterday, there was some discussion about baryon number violating processes. So processes, for example, where a proton is converted into a positron or a lepton. So this is a prediction of the standard model at sufficiently high magnetic fields. And naively, the magnetic fields you need for this are higher than what you see here, but there's quite a lot of uncertainty due to the time dependence of the magnetic field. I was wondering, could you see such a process if a proton were to be converted into a positron experimentally? Do you have any idea whether or not you could, or how you would try to observe such a process?
Oh, difficult question to answer now, but I'd like to take your comment offline, and I'd like to consider, but sorry, I don't have any answer now. But
Yeah, sorry, it was a curveball question, but anyway, thanks.
yeah, but I mean, good time to think. So yeah, thank you very much.
Okay, let's end this with this very hard question, and thanks a lot for your nice talk.